All right, so if you recall from the last section, we were trying to find areas under curves, and we were, although we never had the time to go through the Riemann sums, right? Just because of this the crazy semester that we found ourselves in. We were still doing some of the preliminary work of trying to find areas under curves without really tying it into the integration. It looked like integration, but for example, if you recall these two problems from the previous video, but because we didn't know how to use this definite integration and techniques yet, we were at first drawing geometric curves. Right, we were drawing geometric curves, and then we were hoping that the curves that we drew had a readily available geometric formula that we could use to find the area under that curve bounded. So we found that the area of the following of part A was 8, if I recall correctly, and if the area under part B, I believe, was 21 over 2. And now what I want to do is I want to show you how you can use your methods of integration, right? Your methods of the antiderivative, coupled with this idea of thinking of area under curve as the change in y, coupling those two together to find the integral, right? So this is what we call definite integration. Right, as opposed to indefinite integration. But as of right now, we know nothing. We're just going to begin. So let's start by using the techniques that we learned in at the start of chapter 4 to integrate the following. So we want to integrate 4 with respect to x. Okay. So if you recall, when you integrate 4 with respect to x, this is the antiderivative technique that I taught you was would yield 4x plus c. Okay, so that would be an easy indefinite integral indefinite integral to do. And now all I'm going to do is show you how to apply that with these bounds from 1 to 3. So at this stage, you have your antiderivative, 4x plus c. And the notation that you're going to see me use is we're going to have some type of open bracket here, of which we're going to have the lower bound here, the 1, and the upper bound here, the 3. And what we're going to do is we're going to take 3 and we're going to plug it in for x. And we're going to take 1 and we're going to plug it in for x. And we're going to subtract them. So this is going to be f of 3, right? Meaning I'm going to plug 3 in to my antiderivative, minus f of 1. All right. So I'll finish that up in just a second. Let me go ahead and set up this one as well. So if I want to integrate from 0 to 3, and this time I'm integrating x plus 2, and we are integrating with respect to x. Let's go ahead and get this antiderivative really quickly. So if you want to integrate x with respect to x, this would be x squared over 2 plus, all right, now if you want to integrate 2 with respect to x, this is 2x. If what I'm doing right now, if you have forgotten this, if it's been some time since you've watched that video, you really should go back and brush up on those techniques. It won't take you long, 5 minutes, 10 minutes, then come back, because otherwise you're just writing things down and in hopes that it'll make sense in a little bit from now. So and then we would have our plus c. And now from here, I'm just going to use this new way of denoting the bound from 0 to 3 as having my lower bound here, my upper bound here, and then I'm going to be asking the same question. I'm going to be asking what would happen if I plugged 3 in for x, minus what would I get if I plug in 0 for x. Okay, so let me now come back over to this first problem and let's see what happens here. So f of 3, this is going to be 4 times 3 plus c, minus, now I'm going to plug in 1, so this would be 4 times 1 plus c. All right, in other words, this would be 12 plus c minus 4 plus c. All right, and now we're going to drop these brackets, and of course we're going to make sure we subtract the 4 and subtract the c. So that leaves me with 12 plus c minus 4. Now this would now be minus c. All right, well, you can see that the c's are going to cancel out, the positive c and the negative c. And I'm left with just 12 minus 4, which is 8. Interesting, because that is what the area was as well. Okay, so let's do the same thing here. Now, this would be 3 squared over 2 plus 2 times 3 plus c. I'll go ahead and put a vertical line down here. Minus what? Minus 0 squared over 2 plus 2 times 0 plus c. All right, so this would end up being 9 over 2 plus 6 plus c minus, well, 0 squared is 0, and 0 over 2 is 0, plus 2 times 0 plus c. So let's go ahead and drop our brackets here, and we have 9 halves plus 6. And you can see that this positive c is going to cancel this negative c. So 9 halves plus 6, which is 10 halves, right? Fairly positive that's 10 halves. But it's late, so I will check it. Yeah, so 10 halves, which is 10 halves is 21 over 2, which again is interesting because that matches the area. Now, what can we take away from here? So first off, that's actually a lot faster, right, than trying to find geometric formulas. And of course, we didn't even discuss, well, what happens if you can't find a geometric formula? What are some techniques that would be used? Because we're in a rush, I'm not even going to show you the proof of this next theorem, what we call the fundamental theorem of calculus, which does kill me, by the way, that I don't get a chance to show you. But let's get to it. So the fundamental theorem of calculus, this is just beautiful that these two topics, areas under curves and antiderivatives, separated by millennia, have this relationship where you can think about the integral as the change in y, just like we were thinking about areas as the change in y. And this is what we call, so if I'll read it to you, so if a function is continuous on a closed interval from a to b. Now that closed interval from a to b, that's because you have to have a starting point and a stopping point under the curve, right? You need to bound, just like, remember the rectangle? It has to start at A and stop at B so that we have walls that we can bound our area. Now, And f, is the antiderivative of well, in this case would be our little f is our derivative on the interval a to b. Then we get to make the following remarkable statement that I offer to you without proof. And it is as simple as what we have done on this previous page. And in fact, henceforward, there's no need to have this plus c because they are always going to cancel, right? When you do, so I want to make sure if you, right now, listen to me. If you do integration that looks like this, there's no upper bound or lower bound, you are always going to have plus c. If you do integration that looks like this, then you're going to have, my apologies, that slipped away from me too quickly, where you have upper bounds and lower bounds, you are never going to have plus c. They are always going to cancel each other, okay? You're going to get a finite number, if the integral, obviously, if it exists, if it converges, but you're going to get a single number that can be interpreted as the area under a derivative, or could be interpreted as the change in y. Now, let's spend the rest of this video just practicing this technique really quickly, okay? So what's going to happen right now is I'm going to rush through the integration because I've already taught you integration. I don't have time to teach you the integration again. If you need to go back to 4.1, then you'll have to go back to 4.1. But let's start with part A. So I'm not going to have a plus c because I see that this is definite integration. So let me go ahead and do this. So this is going, if I integrate, we're going to have x cubed over 3 minus 3x, to which I want to back substitute. I want to use that fundamental theorem of calculus from 1 to 2. So remember, it's from here, it's always f of 2 minus f of 1. And that minus symbol is important because if you don't use the grouping symbols, you might find yourself in trouble. So when I plug in the 2, when I plug in the 1, I know you know how to do that. You're going to end up with 8 thirds. Oh yeah, let me just go ahead and write. What you're going to end up with is 8 thirds minus 6, which is equal to negative 2/3. Now, I understand that you might be thinking, well, how the heck do we think about negative areas? It's a very good question, but right now we're more focused on the technique of this fundamental theorem of calculus, right? So part B. Again, you would turn that square root of x to x to the power of a half. And in fact, I'm going to bring the 3 out in front of the integral. And as of right now, I'm going to go ahead and write that as x to the power of a half. All right, so let's go ahead and finish it. So now we're going to have 3 multiplied by, whenever I have a constant multiplied, I use a double bracket just to remind me to multiply by the 3. And x, a half plus 1 is going to be x to the 3 halves over 3 halves, to which I want from 1 to 4 as my bounds. So now it's f of 4 minus f of 1. All right, the result that you get, remember that's just, you got to plug in a 4 for the x 3 times and then multiply by the 3. Then you got to plug a 1 in for the x, do your division and then multiplication, exponent, then multiply by 3. What you end up with is well, I have written here 14. Now, yeah, so I have 14, I think, and that should be correct. All right, let's go ahead and look at part C. All right, so now we are, and I'll go ahead and write part C since it's a little bit far removed from above. So we're going to be integrating from 0 to pi over 4. And what are we integrating? We're integrating secant squared x. Okay, so this is definitional. Okay, this is definitional. The integral of secant squared, it would be tangent. This is tan x. I still need to go from 0 to pi over 4. All right, so now it's f of pi over 4 minus f of 0. All right, that ends up being 1 minus 0, or just 1. Okay. So far so good, right? This is not bad. This is not bad at all. Why don't you, let me read this question to you, okay? Make sure you understand it. And then why don't you try it on your own? Pause the video if you want, and then I'll come back and I'll guide you through the rest of it. So we're asked to find the area of the region bounded by the graph of. Okay, now, as soon as you read that, you should be thinking the definite integration, right? So you want to find the area under a region bounded by, so we should automatically be thinking definite integration, but of course we're going to need to know what to put here and what to put here. And since it says find the area of the region bounded by the following graph, meaning the area stops here. Well, remember, we're always finding areas under under derivatives, right? Under the graphs of derivatives. So that 2x squared minus 3x plus 2 is going here. And then it's going to be with respect to x. Okay, now, so the area of the region is bounded by the graph, right? So here is your graph. So it's bounded by the graph, meaning it doesn't go above that. It's also bounded by the x-axis, meaning it doesn't drop below the x-axis. And it's bounded by the lines x equals 0 and x equals 2, right? So here's the vertical lines x equals 0, and here's the vertical line x equals 2. So that shaded region, that pink region, is the area that we're looking for. Okay. So I would suggest that you pause the video for a second and see if you can actually do that. All right. So I'm going to assume that you tried it. You probably didn't. I know you didn't. That's okay. That's all right. We're going to keep rocking. Ready? So the area in this case is going to be, let's go, well, first off, if we're bounded from x is 0 to x is 2. So from 0 to 2. All right. Let's see how you did. So if you integrate that, we would get 2x cubed over 3 minus, well, we got 3x squared over 2 plus 2x. And we don't need the plus c because we know when we do the definite integration, the c's are going to cancel. We want to go from 0 to 2. All right, so now it would be f of 2 minus f of 0. So there we go. So we're going to plug in a 2 for x. That should be 16 thirds minus 6 plus 4 minus, well, if you plug a 0 in for x, you just get 0 plus 0 plus 0. So we end up with 10 thirds. Sorry for this little line right here. So an area of 10 thirds. Now, I don't know what units we're using, but it's 10 thirds units squared, okay? Now, I do understand that it's probably fairly easy at this stage to just write this off as just another recipe that I have to learn to get to through my degree, and I get that. But can you understand how unbelievably helpful this would be? I'll give you an example. Let's say you own a lawn mowing company, right? And now you can pull property lines up, right? You can pull property lines up online. And let's say every time someone calls, that you give free estimates. That's a lot of time, energy, and cost for you to ride out to this individual's home, so that you can give them an estimate about what you would charge to mow their lawn. Now, what if you were able to pull their property line online? Okay, now maybe it looks something like that, but hey, you know what? You actually know how to take areas under curves. So you went through and you found the area under that curve. So now you actually know, you got the customer on the phone and you were able to go through a little bit of calculus. You actually know how much area that you would be mowing. You still don't know exactly if you're dealing with how many trees are in the property. You don't know how many you don't know the layout, so you still might get a little bit more information before you start quoting. You might say this is a tentative quote, but does it not make sense that just armed with a little bit of calculus, you would be able to figure out the area of this individual's yard without ever driving to their yard? Interesting. What about if you had to? What about if you planted some type of garden region, right, and it had some odd shape like this, and you were able to figure out how much mulch or how much fertilizer or whatnot that you needed, again, without a geometric formula to plug into. If you had to replace a piece of sheetrock, right, out of your, and you knew what the cost of that. In other words, at least, even if you do write this off as just another recipe for you to learn, at least recognize how this could be helpful, right? This has so many different applications, and we haven't even yet begun to study them. So I'm going to go ahead and leave it at that for this first video, and I'll be back. We're still going to be in 4.4, but this will be 4.4 Part A. I'll be back for 4.4 Part B.